there, you can go ahead.
Okay, well, yes, thank you for the introduction, and thank you to the organizers for allowing me to give this talk. This is actually the section of tomorrow, bioinformatics, data analytics, and applications. But I was actually planning to be outside of the internet tomorrow, but that got canceled. But it was better to not mess up the schedule that I already messed up because of my plans. So we'll start this section of tomorrow with this talk. And well, this will be about space filling curves. This is a joint work with Markus Jahn, who works in geoinformatics. And most of what I'm talking about today is published in this paper from last year in the Computer Journal, which somehow still does not have a volume and a page number. They seem to be slow on that, I guess. But anyway, let's start with the contents. First, an introduction, and then Hilbert curves, and then p-Adic gray code. That is what you need in order to extend this idea of Hilbert curves to, in a meaningful, in one way, to higher dimensions. And then you get the p-Adic Gray Hilbert curves. And with this, you can produce an index, a scaled index, or a method for indexing. And we'll discuss locality properties of this and look at some experiments and possible application, and then conclusions. So introduction. In 1877, Cantor proved that the cardinality, just the cardinality of the real line, is the same as the cardinality of n-dimensional Euclidean space for any natural number greater than or equal to 1. And that was a surprising result, I guess. But when you introduce topology, there was another surprising result, that namely Peano found a continuous bijection between the unit line into the unit square. And his method, you could call this already a p-Adic space filling curve. He did it by trisecting the two coordinates of the square, and then iteratively doing this in such a way that you could obtain a curve which fills the squares, the little tiles, as being parts of the curve, and then iteratively finding then in the limit a curve, a continuous function. And in 1891, Hilbert does this in a similar a way to do a binary construction of such a space filling curve. So you have a p-Adic space filling curve. And then later, higher dimensional realizations of these ideas became realized. And the method was the gray code. And then you can ask, how many are there? Well, I will not really count them, and there are some open questions, I think. And anyway, there are lots, depending on the dimension. It increases with the dimension. So the idea of Hilbert curve first, I'll explain this in the first two iterations of this. So you have your square, and then you take the half of each coordinate axis. Then you get, that means you get 4 smaller squares, and then you pass through those squares in a curve that from left, bottom left, going this way up, and then to the top left. That's the first iteration of a in a coarse scale, a curve. And then the next iteration, you subdivide each square again, and then you follow coarsely this short segment with another copy and rotated and reflected of this first iteration Hilbert curve. So you want to move along this lower left big square, and you pass through these little squares in this way. So you twisted this, you turned it and reflected it so that you start here at your lower corner, and then you can connect into the next square, which is this one, the next big square, and the bottom, and so on. And you can do this. You can find reflections and rotations of copies of these things in order to make them in a smaller scale and connect them to a bigger next iteration space filling curve, and so on. You need to take the limit of this process, that is your Hilbert curve. What you can do is you can organize this in a tree. If you start with a big square, this is this big dot, and the root of the tree is that big square. And then you subdivide each coordinate, and you have to choose an ordering of the coordinates. You do this locally. So first you have this, subdivide the y-axis, and then the x-axis, and then you get your 4 dots here, which are the 4 little squares in the big square. And then you continue this again, and here you have different subdivisions. For first the x, and then y, and then here later you have first y, and then x, and so on. You can find an ordering of the coordinate for which you do your subdivisions. So and then you have your space filling curve, and your points will be, you go through those leaf nodes from left to right, and this follows this curve here. I will explain this rectangle right now. This rectangle corresponds to this path. So each vertex, or each path, which vertex corresponds to a path from root to that vertex, and each path or vertex corresponds to a rectangle, and this blue path corresponds to this blue rectangle. And Hilbert curves have a nice locality property. That means that points nearby in the curve are also nearby on the square. For example, well, here are 2 nearby points, and they're nearby on the square, but the opposite does not, the converse does not hold true, of course, because here these 2 squares, they are nearby on the grid or in the square, but not on the curve. From the curve you have to go quite a few steps until you reach those 2, can connect those 2 points. Now, a p-Adic discrete curve, that's when you want to have general, not 2 or 3, like piano. You can have any p, which p doesn't have to be a prime number here. I would just call it p because it's a p-Adic conference. So any natural number. What you have is a bijective map between the first p to the r numbers and to the grid z modulo p to the k z and r copies of that. And this is a p-Adic discrete curve of order k and dimension r. So r is the dimension, k is the order. If 2 neighboring indices get mapped to 2 neighboring points, in a sense that, the tiles are neighboring, that means the coordinates differ the difference is only in 1 coordinate. All other coordinates are the same. Or in other words, the Hamming distance is 1 for 2 neighboring points. And then you take the set of all such p-Adic curves, order k and dimension r, called CKR. And now you take such a curve, and then you define the so-called C-automorphism group. These are just the permutations, of the symmetric group of this n r-dimensional grid, such that curve points get mapped. A curve gets mapped by this automorphism to such a curve also. This is the C-automorphism group. So for a fixed curve C. And what you have is an operator called refinement. So you just take an R tuple in this r-dimensional grid and map it to the kth level by just taking, it modulo p to the k, where you multiply each coordinate with p to the k minus 1. That is just, you map this coarse tuple, which corresponds to a coarse point in this refined grid, to the lower left corner of each, if you visualize each point as a cube. So you maps each point to the lower left corner in the higher levels. And you have a projection operator. Just take what you have modulo p to the k, make it modulo p, And with these two operators, you can construct iteratively more and more refinements of a fixed curve of level 1. So this is how you do it. You use this, you see those, here's a pi, and there's, I forgot, one of those pies has to be of the other kind of pi. I mean, this one here, refinement. There's a typo here. So this is the construction that you do it. And then you get a so-called Hilbert family if you just iterate this process. So what you have is you fix a number of C automorphisms for your starting curve in the first level. And then you take copies of these, and you, with the automorphism, get other kind of curves, and then you glue them together. And this is your Hilbert family. I'll explain this in this picture. Here you have this first iteration of your Hilbert curve. And then you have a tau, a family of reflections and or rotations. And so in 4 in this case, and then you can use these for the first one here, and then the second one here, and the third one here, and then you get here. And if there's reflections and there's automorphisms are correct, you can glue them here together to obtain the next level curve. So the problem is, does this exist? And the answer is, well, if P is odd, then any first level curve can actually generate a genuine Hilbert curve. It is the generating curve of a Hilbert family. The idea is because you have two opposite corners of the hypercube, and they can be connected by a discrete p-Adic curve if P is odd. And this allows you to construct these automorphisms such that you can make a Hilbert family. And if P is even, there's a restriction on the existence. You have to have that your beginning point and end point are not opposite corners. If that's the case, so the Hamming distance is less than R, then that is then that's what you have to have. If they're opposite, then it doesn't work. And an open problem is how many different kinds of p-Adic Hilbert families are there modulo the automorphisms of the R hypercube. Now we come to the p-Adic gray code in order to construct a certain type of Hilbert curves. First, the 2-Adic reflected gray code is you take a binary vector and superimpose it with its right shift by 1, and then add these two numbers modulo 2 together, and then if you do that, you obtain a reordering of your binary numbers. Instead of the usual 0, 1, 2, 3, I mean 0, 0, 0 in the 3-dimensional case would be next one 0, 0, 1. That's okay. And then the gray code makes it that the next one will be 0, 1, 1, and so on in this ordering. And you will observe from, if you look at two neighboring of those 3 tuples, that they differ only in 1 digit. So the Hamming distance is actually 1 for 2 neighbors, and that's a curve. And the starting point is always 0, 0, 0, and the end point is always 1, 0, 0. So the start and end point in this case will always have a common edge in the hypercube. So they're very far from opposite to each other. And in the p-Adic case, if P is odd and greater than 2, what you do is this: you have your number, your vector 0, 1 to P minus 1, and then you take iteratively 0 times this previously constructed gray code, and then 1 times the Cartesian product with the same code that you constructed before, but in reverse order, and so on. You alternatively do this, and then you get, visualize this here in this example, G23. So you pass through these first 3 points in this from left to right, then go up next one, and then from right to left, go up next one, and so on. This is this process of alternatively reversing the gray code that you had before. And you will observe that start and end point are always opposite corners. This is in general the case for this p odd. If p is even, you do the same thing, also with the alternatively forwards and backwards of the previously constructed gray code, and you will always end up with being reverse order. That means your start and end point always have a common edge. And then, in order to construct the curve in the next iteration, you need a transformation. Namely, it's an affine transformation of a special kind. You have the translation here, but here is the linear part is just a permutation of coordinates. And then you could construct what I call affine p-Adic Gray Hilbert curves. So the construction goes like this. If you start with your hypercube in one level, and then you say you have two sub-hypercubes which are consecutive in the next subdivision. And then in the case odd, you choose an ordering of coordinates for your left, the first one, A, and then take this gray code and go up to the endpoint FA, and then this FA is opposite to the starting point. That means it neighbors, because you start in the left corner and the next one is on the right of the block is on the right of the first block A. So the opposite corner will be a neighbor of the next block B. So then you can continue with this. And if P is even, you have a corner of A. FA will be the corner of A neighboring B, such that FA is different with the origin of A only one coordinate. And then you choose the ordering of the remaining coordinates, and this corresponding gray code will always end in FA. And then you continue by taking the union of those two hypercubes, and EB is a corner which neighbors the endpoint of your previous the gray code that you had in E, and then you bring up the origin via translation, bring up the origin of this ZPN to that point EB, this chosen point EB, and then you continue the whole process with your second block of big hypercube B and the neighboring big hypercube C, and so on. And in this way, you could guarantee that you always glue them together, and then you obtain a Hilbert curve. I mean, the next iteration of a affine p-Adic Gray Hilbert curve. And since you can choose very many orderings of coordinates, you will have an exponential number of possibilities in the dimension. Now, in order to obtain a indexing method, well, let's look at the p-Adic Hilbert curve index. So the traditional way is a static way. You take all the leaf nodes you could forget about the tree in the traditional way, where the tree helps us to improve the traditional way. So that what we call that a static Hilbert curve index. And your data is perhaps just a sparse point cloud, especially if the dimension is high or you have a high number of iterations. Then you have very many small cubes subdividing your big cube, but your data points occupy only very few of these cubes. Here they're represented by 3 points A, B, and C. And if you take the paths to the root upwards, you will get a subtree, and all you need is this subtree. So, and the other leaf nodes are not filled. They're, especially as the depth is high, then you have lots of empty leaf nodes in your tree, and you can remove all superfluous vertices of the tree, and then you get the so-called minimal subtree, whose end points or whose leaves are the data. And since you have used the Hilbert curve ordering, you have an ordering of your data. So your curve passes through these data points, and you just remember these data points. And so this is a very space efficient index substructure of this big static tree. We call this the dynamic or a scaled Hilbert index. And this has efficient insert and delete and retrieve methods. If you can visualize this in order to look at locality properties. You take a normal distribution in 3-dimension, sample it, a finite sample, and you can choose there is, as I said, a degree of freedom where you choose permutation of coordinates locally. And one version of doing this we call this bubble, and another will be called ring. But the differences are not very big in 3D. Here is the static tree up to a certain level. You see it's regular, and here is in 3D the cube, where the points get passed through by this 2-Adic Hilbert curve. In the dynamic version, you see that the depth varies because some points are more dense locally and some points are less dense locally. And then here is the curve, the corresponding curve, which contains only the data points in p = 2. And for another different kind of choice of coordinate orderings, you get slight differences in the tree structure or the path structure. So, and p = 3, again static and versus dynamic, and the same algorithm for producing coordinate orderings makes some small difference. Here's p = 4, 4-Adic tree. You see here the density is more on one side and less on one other side of the tree, of the dynamic tree. P = 5, similar phenomenon, all normally distributed points. And in order to look at locality properties from a more theoretical point of view, we have finite point cloud in the n-dimensional hypercube, and we consider the nodes of the Gray Hilbert tree, particularly the leaf nodes of the Gray Hilbert tree, as buckets, which can either be empty, filled, underfilled, or overfilled. Underfilled or overfilled is with respect to some bucket capacity, s greater than 0. And you count the overfilled leaf nodes of the tree and divide it by the number of non-empty leaf nodes. This gives you an omega, and then you can we define a number which is called the capacity of the tree for the data S. Is just the number of leaf nodes multiplied 1 times 1 plus this omega. And the idea is if one leaf node is overfilled, then why can't all the other leaf nodes also be overfilled? So the capacity of the whole tree increases by this amount. And then you can look at, if you want to compare different trees, you can look at the capacity ratio. This omega divided by omega of the other tree. This is the ratio. And we will compare the static tree. The static tree is the regular tree with lots of, possibly lots of empty leaf nodes, but with maximal iteration number given by this number. And the other tree is the scaled Gray Hilbert tree for the data S. The motivation for this number k is that you want, well, p to the nk, the number of leaf nodes, be roughly the number of data points divided by the bucket capacity of each leaf node. And you want that as the number of leaf nodes in your static tree, so that on average, no leaf node is overfilled. And so your k, the iteration k, is this number here plus some epsilon between 0 and 1. And if this condition is so log s over n is smaller than this epsilon here, then the scaled tree is more storage efficient than the static tree. And relative efficiency increases with increasing dimension n. That means for fixed n, so this is the case if bucket capacity S is sufficiently small. So the idea of the proof of this theorem is that what is the meaning of these numbers? So you have the ratio of these omega between the t scaled and t static. It tends to 0 for n for increasing dimension, and this epsilon number here, this little epsilon, it converges to 1 for n to infinity, and that means that the bound, this ratio can be made to be less than equal to 1, because so that means that the scaled tree is more storage efficient than the static tree. And from this we can construct another number. We call this p-Adic, the Gray Hilbert local sparsity measure, which normalizes everything so that you have a number between 0 and 1. And this depends, we think that this quantity depends only on the distribution of S if the bucket capacity is fixed. We did some experiments. In the paper, there's another data set, but I'll discuss just the iris data set from Fisher in 3 different encodings. First, the original, the raw data. This is a data set embedded in 4 dimensions. So you have 4 attributes. And another coding of the data, which is called by Fionn-Murtagh complete disjunctive form. Its embedding dimension is 400, and its coordinates are just 1s and 0s. So it's just you have an entry or not, and then the embedding dimension becomes 400. And there's another coding that we use. It's called BCH. Those are 3 authors, 127, 50, 27, and its embedding dimension is 431. And here's a result for this measure rho p, depending on p, and the bucket capacity on a logarithmic scale of powers of 2. And you see, well, the different measures vary with the bucket capacity, but they somehow get closer to each other. And it doesn't change much if you change the ordering of the local ordering of the coordinates. But for the so that was the raw data, 4-dimensional encoding. But for the high dimensional encoding, you will see that you just have 1 point either black or 1 point red, because the quantity omega here, the small omega, is 0. The data is so sparse that you will never where are we? That there are no overfilled leaf nodes, so there is no dependence on the bucket capacity. Not the bucket capacity, on the prime number. On the prime number, there's no dependence on the prime on the p. P is not prime. There's no dependence on p, just on the bucket capacity. And the higher dimensional encoding has a higher rho value. It seems to tend to have that than the slightly lower dimensional, high dimensional 400 CDF encoding. So what do we have? In our experiments, we've seen that high embedding dimension means local sparseness. And in this case, our measure is independent of p. And Fionn-Murtagh had already observed, in this case of high dimension, encoding of data, that the ultrametricity of the data seems to be high in that case. And we can ask for a relationship, is there a relationship between our local sparsity measure and any measure of ultrametricity? And the last topic on this idea of Gray Hilbert curves is partial differential equations on graphs or directed acyclic graphs, which are in Euclidean space. So you view a gamma, a directed acyclic graph whose vertices are in the unit embedded into the unit cube, and E is just the edge relationship that you have from the graph, and T is a p-Adic Gray Hilbert curve index for those vertices. So you see your vertices of the graph as a point cloud with an index of p-Adic structure on it. And then you have the tree, and the leaf nodes of the tree define p-Adic disks. So these are just finite expansions of a p-Adic number which could continue in some way in very many ways. So you have a disk. And what you can do is look at the p-Adic graph Laplace operator, which Wilson talked about last year on the last p-Adic conference, and then study the dynamics of the graph of that the Laplace operator in parallel using this index method. The idea is to do a parallel computation for partial differential equations. I remember there was a controversy or a misunderstanding in the last conferences, because somebody thought that he embedded the whole graph into the p-Adics, but it's not the case. It's just the vertices are given p-Adic coordinates, and then you take the adjacency matrix from the graph and make it into a Laplace operator, which is a p-Adic Laplace operator. An example for such a directed acyclic graph would be a convex polytope complex embedded in R to the n, and the vertices would be just the centers of the polytopes, and edges come from the boundary relationships, which are bounded by the next lower dimension of a polytope. And you can give them weights if you like with the polytope volumes or so. An example scenario would be, say, in the domain of geoinformatics, city models, if the detail is not too large, because you don't always have convex polytopes. And an example PDA would be, for example, heat flow through buildings and their parts. And I'll explain briefly the p-Adic graph Laplace operator that you get from such a finite graph with a vertex at V. You just give p-Adic coordinates to the vertices, and then fix a small enough ball around each vertex, p-Adic ball, such that these balls are disjoint, and then take the union, okay, which we call Kn. And then you have, if you have n vertices, you have your adjacency matrix, C to the well, it's not complex value, but it could be a square complex n times n matrix, and you make out of a matrix a function on pairs of those domains Kn, which are just these disjoint balls, unions of disjoint balls. So from a matrix, you make a function by taking summation over all the vertices twice, and then take here the matrix entry and indicator functions for these balls. And the graph Laplacian is just a special case, and that corresponds to, well, you have A times minus some degree matrix, corresponds to this operator, like linear operator, by taking the usual integral with the A matrix, A function from the matrix, times uy minus ux dy. So, where the integral is restricted to Kn. This is Zuniga-Galindo's p-Adic graph Laplace operator. And conclusion, so we have a theoretical approach to p-Adic index structures. We have a gray code which gives rise to a higher dimensional Hilbert curve and any P. We get a tree, which gives, and a linear ordering of nodes with nice locality properties, and we have lots of index structures which you can construct with this method. And we have a measure for the sparsity of a point cloud, and potential application would be p-Adic parallel solver for p-Adic partial differential equations on graphs or different diags with vertices in Euclidean space. And future work, which we hope to have, is p-Adic approach to flows on city models. And what is in review or already accepted is p-Adic wave equations on finite graphs and T0 spaces, where it made a dictionary of how to have graph theoretic functions or vectors and matrices, and corresponding to p-Adic functions, and looked at solutions to p-Adic wave equations and on finite graphs. And yeah, thank you. That was the end of my talk.
Thank you very much, Patrick, for a very nice talk. Let me stop the recording and let's find out if there are questions or comments.